Thank you, Gemma. I have only 15 minutes. I got rushed, so I go through briefly what I'm doing with my with my colleagues. Okay. I will talk about a version of isogeometric analysis applied to fracture mechanics analysis. Okay, the contents of my talk are listed here. First, I talk about motivation and objectives and some of the formulations, then come to some example problems. Okay, first, let me introduce what is isogeometric analysis. Roughly speaking, we replace the shape function of finite element by B-spline functions or Nernst functions, which have higher continuity than Lagrange type interpolation functions used for finite element method. Then, because of the higher continuity as such, and also CAD geometries are represented by Nernst function exactly. Therefore, we can avoid geometrical error, which is inevitably associated with finite element models. Okay, this is IGA model, very smooth. Then it is more accurate than finite element method because of higher continuity in interpolation functions. Then when we talk about crack analysis, we developed a methodology called as singular patch method, which is very similar to Barzom's singular element in finite element that can exactly reproduce 1/square R type singularity at the vicinity of crack tip. So that when we performed some analysis, the solutions were very accurate. However, IGA have some problems. When you perform crack analysis, you need to refine your model locally. However, when you have IGA or B-spline volume, that is very similar to a sort of super element in the sense of finite element. You have problem in localized refinement of the model, so that typically what called the XIGA, which is to make use of enrichment function to introduce the crack, or T-spline functions, which can localize the refinement. However, we think that there might have some room for us to develop some other technologies. Okay, that is motivation of our work. So we took the idea of S method, which I will introduce shortly, combined with IGA. Okay, so what is S method is summarized in this slide along with IGA. Okay, here is the boundary value problem. Okay, with some notch here. And in S method, what we do is that we have one IGA model or finite element model representing full structure, and another model that represent localized feature superimposed each other. Okay, when in terms of interpolation functions, what we do is that in this region where models are superimposed, the displacement functions of both the models are superimposed. Otherwise, the displacement function of global model alone is used. Then we need to satisfy at least C0 continuity at the boundary here. To do that, we just set the displacement out of this local model to be 0 here so that we can satisfy Caesar continuity. Then we just plug these conditions into the weak form, which is anyway principle of virtual work. And we perform some algebra that is very straightforward, plugging the superposition of global and local displacement field. Then we can separate equation for global model associated with variations of displacement of global model, and another is associated with the variations of displacement of local model only. Okay, that is very simple. Then we can apply this technique to crack problem. In crack problem, the crack can be modeled only by local model. Therefore, if you had global structure already modeled, then you can just plug, say, local model that is exclusively for the crack. That's it. However, there is one problem that is the generation of coupling stiffness, which couples the deformation of global and local finite and local IGA model, which is in this shape. Okay, B is ordinary B matrix, stress strain relationship, and for local and global. What is problem is that whatever you do, you have, in this particular case, one element in local IGA model spans two or more than two elements of global IGA model. Although I claimed that IGA has a higher continuity than finite element Lagrange type interpolation function. The function representation switch at the inter-element boundary, though functions are continuous, but functions shapes change so that when you apply Gauss quadrature, you have certain problem. But if you had finite element, you have only C0 continuity, you have kind of step function in terms of displacement gradient. You have severe problem. Anyway, let me go over fracture mechanics applications. To compute J or interaction integral to extract stress intensity factors, we just used ordinary domain integral approach. Okay, and I skipped all the details. Domain integral approach is very popular in the application of finite element method as well. However, in IGA, we have coarser discretization than finite element case. This is crack face, so that we do not perform the domain integral based on elements. Instead, we set thin slice-like integral domain apart from IGA element. Then this thin slice-like integral domain moves along with crack front so that we can extract continuously changing stress intensity factor or J integral values. Okay, and let us check the example problem. This is simple embedded elliptical crack, mode 1. So in the model, ideally the crack is embedded in infinite elastic media, but we cannot do that in numerics. So that the crack is embedded in a very big elastic body, and this is global model and local model is plugged there. Then we used cubic-based functions and we compared our solution with analytical solutions for infinite body. This is one typical IGA model. This is global IGA model. At this position, local IGA model is plugged in. And these lines show the inter-element, inter-patch boundary as such. And the thin lines represent boundaries of IGA element. All right, this is the case of, these figures show the error in the evaluated stress intensity factors. At the top, this is penny-shaped crack. At the bottom, elliptical crack, whose aspect ratio is 0.1. This is a very severe case. In both the cases, error is very small, especially for this. At this point, it is difficult to evaluate stress intensity factor accurately. However, in your case, error is very small, less than 2%. And we have done various cases. In all the cases, we could obtain stress intensity factors very accurately along the crack front, comparing with finite element case. Anyway, let me go further. Why doesn't this thing work? Oh, okay. Okay. So this case is a mixed mode case. We just tilt the local model so that we can easily produce mixed mode problem. Then, okay, this is global model, local model, and tilting, right? Then this case is tilting angle is 45 degrees, and we have all three modes. Okay, this is penny-shaped crack. Again, okay, very thin crack. In both the cases, stress intensity factors computed by, in this case, interaction integrals were very accurate. Then we extended the methodology to the computation of finite strain elastic plastic case. This figure shows basic formulations of finite strain elastoplasticity. Okay, this is still underway, but as initial indication, when after we perform several analysis, okay, we can we know that we can compute finite deformation analysis under of elastoplasticity. Okay, this is a summary of my talk, and due to the time constraint, I skip this slide. Okay, I am happy to take questions, comments.
Okay,
Thank you very much.